Okay, looking at Chapter 11, we're going to take our annuities and we're going to calculate the periodic payments for our annuities. So on our calculator, we're going to be calculating the values in our payment button. Up until now, they've only been inputs. Now we're going to get them as an output. So looking at annuity, we have a present value, a future value, we have a bunch of payments and an interest rate. We're now going to be calculating what the value of those all identical payments are for this annuity. So we'll start off with page 433, number 12. So we have number 12. It says, Brenda and Tom want to save $30,000 over the next 4 years for a down payment on a house. What amount must they regularly save from their month-end paychecks if their savings can earn 5.5% compounded semi-annually? So we're going to do semi-annually compounding and monthly payments. So doing the picture for this, we're creating an annuity that we're starting with 0. We've had no savings so far, and in the end, we want to have $30,000 as a down payment. So you want to be able to withdraw $30,000 from this annuity to get a down payment. And we're going to do this starting at time 0, and it's going to end in 4 years. So over 4 years, we're going to do this, and 5.5% compounded semi-annually. And we know that these payments are going to be monthly. So what we're looking at is we're going to take the monthly payments and the 4 years to determine N. We have a present value, which is 0, a future value, which is $30,000. That's our goal. We have an interest rate per period, which is 5.5. Compoundings per year, which was semi-annually compounded, so twice a year, 2. Payments per year, which is monthly, so monthly relates to 12. And an N, which is number of years, 4 years, times by the payments per year, 12, so that's 48. And we're going to compute the payment this time. We're going to find out what payments are required to take $0 to $30,000 over 4 years. So putting this into the calculator, we get 0 for present value, 30,000. Again, it's going to be positive because we want to get that value in the end, future value. 5.5 is our I per Y. We're going to do second function I per Y and to say our payments per year are going to be 12. And that's automatically going to change our compoundings per year, so we need to set that to be 2. And I'd like to go between payments and compounding to make sure that it's right. We now have an N of 4 times 12, which is 48. That goes into our N. And we're going to compute the payment to be negative $560.90. So they must save $560.90 per month. Big thing to note here is this N is going to be related to payments per year. And the payment is going to be the amount that relates as well. So the payments are going to be monthly as an output. We're going to take a look at also question 14. And question 14 says, the RBC Royal Bank approved a 4-year $20,000 Royal Bank buyback car loan to Zaman at 7.5% compounded monthly. The monthly payments are to reduce the balance on the loan of the Royal Bank's guaranteed buyback value of $72.50, and you want to calculate the monthly payment. So again, we're going to create our diagram. And in this diagram, we're going to start out at $20,000. We borrowed $20,000 here, and in the future it's going to be worth $7,250. We're going to make 7.5% compounded monthly. And we want to know what the monthly payments are going to be. Well, $20,000, $7,500, we're going to make this. We get the benefit of $20,000. We'd have to pay back the car at the end worth $72.50, so it's going to be a negative value. Again, taking a look at things, we have a present value, which is $20,000. Our future value is negative $72.50. Our payment here is something we're going to find, so that's going to be our output. Our I per Y is 7.5. Compoundings per year is 12. Payments per year is equal to 12. And N is going to be, well, we didn't write this down. It's a 4-year loan, so again 0 to 4 years. 4 years at 12 times a year, that's 48. And we're going to compute the payment to be, well, $20,000 is our present value. It's how much we got in the loan. $72.50 negative is the future value. 7.5 is the I per Y. 12 payments per year, 12 compoundings per year. 48 is the N, and we're going to compute the payment to be negative $353.59. So we're going to have to pay $353.59. Now, this value is the confusing part of this problem. And so what I'm going to do is I'm going to take a look at the two values, and I'm going to say, if this is this value, 353.59, and I'm going to multiply that by the 48, and I'm going to say, we're going to pay about $17,000, which is close to the difference here. It's a little bit more than the $13,000 that we actually paid off, but it's close. If we made the $72.50 positive, which you might do in this problem because it will actually let you do it, and now we compute the payment, it's going to be $613. And if we multiply that by 48, it's going to say $30,000. So that's a huge amount of difference. So this one's probably wrong. Now this is a weird problem because these two are different. So here we're getting a $20,000 loan. We're getting the benefit of $20,000. And in the end, what happens is we would have to pay back not money, but the car. And the value of the car is $7,250. So think of it this way. If we wanted to keep the car, we'd have to pay another $7,250. So this is a payment. That's why this value is negative, because we'd have to pay an additional amount. We're only financing the difference between the $20,000 and the $72.50.